Welcome to this tutorial. In this tutorial, we look into Aspen Plus simulation of a regenerative ideal Rankine cycle with a closed Sweetwater heater. If you don't know what is a regenerative ideal Rankine cycle, please watch the previous video. In regenerative cycle with closed Sweetwater heater, the heat is transferred from the extracted steam to the feedwater without any mixing. So what happens is that you take out some of the steam from the turbine, you put it into a heat exchanger, so no direct mixing, unlike open feedwater heater, and the steam uh, converts to liquid, and the heat is transferred to the feedwater after the pump before the boiler, and then this condensate after the closed feedwater heater goes back to the condenser. Please note that here we need an extra equipment, could be a steam trap or a valve. What happens is that since the pressure of the extraction stream is higher than the condenser, we need to decrease this pressure. And in order to do that, we use this steam trap or valve. And the process that occurs here is a throttling process. Uh, Ideally, the feedwater is heated to exit temperature of the extracted steam, which leaves the heater as a saturated liquid at the extraction pressure. What does this mean? Let's say that the extraction pressure of this bleeding stream is 5 bar. The saturation temperature at 5 bar is 151.8 degrees C according to steam tables. Let's say the feedwater inlet temperature is 50 degrees C before entering the closed feedwater heater at the state 2. Ideally, the feedwater is heated from 50 degrees C to 151.8 degrees C, while the extracted steam condenses and exits at the saturated liquid at 151.8 degrees C, which matching the extraction pressure. Uh, We can look into one example and do this mass and energy balances in Aspen Plus program. Consider that you have a steam power plant that operates on an ideal regenerative Rankine cycle with one closed feedwater heater. Steam enters the turbine at 15 megapascal and 600 degrees C. Uh, and then it's condensed in the condenser at a pressure of 10 kilopascal. 20% of the steam leaves the turbine at the pressure of 1.2 megapascal and enters the closed feedwater heater. We want to determine the thermal efficiency of this cycle, and we assume that the steam flow rate, mass flow rate, is 10,000 kilogram per hour. To start this simulation, please refer to video part 2, setting up a simple ideal Rankine cycle in Aspen Plus. Follow the same steps for defining the property method, setting up the boiler, turbine, pump, and condenser, and connecting the streams. Once you have set up the simple ideal Rankine cycle, as shown in that video, you can modify it by adding a closed feedwater heater to simulate the regenerative Rankine cycle. This will involve adding a heat exchanger block to the model and setting up the stream conditions and extracting the steam and feedwater and adjusting the flow path. What you can do here is that if you remember, we discussed also in the previous video about open feedwater heater when you want to extract some steam from the turbine. You cannot do it directly in Aspen. So what you can do is to perform the simulation is to add an extra turbine and extract some pressure out of that extra turbine. I will add those components to the main flow sheet here, and I pause the video, I add those components, and then we continue from there. As you can see here, now I have added the needed components to the main flow sheet. As I mentioned, I have added one extra turbine. I used a splitter in order to split the flow that goes out from the first turbine and send some part of it to a closed feedwater heater. In this case, it's a heat exchanger. As for heat exchanger, I've used this. If you go to this section below the main flow sheet, you will see the exchangers. I use a like simple two-stream co-current heat exchanger. What happens here is that this steam that comes from the turbine 1 goes to this closed feedwater heater. It transfers its energy to the feedwater and then it goes to the condenser. I also added one valve. The valve is in the pressure changes. Here you will see the different options here. I use the simple valve. And then the water that comes from the condenser is transferred to the boiler. And before the boiler, you see that feed water enters this closed feed water heater and the temperature hopefully rises. We will see that after the simulation. I have named all these streams properly, and now it's time to insert the information that we need for the Aspen to perform the simulation. To proceed, we click on the next button to find out where we need to add the information. We start with the closed feedwater heater. Is the model could be shortcut. We keep the calculation mode as design. The other specification we need here is that we can, if you remember, we said that the steam leaves the closed feedwater heater ideally as a saturated liquid. So what we can do here is that we can specify the hot outlet vapor fraction, the hot stream outlet vapor fraction to 0, which means that we have saturated liquid. And then we click on next. We need the split fraction. We said 20% of the steam is extracted. So we put 0.2 for the stream X EXT. Next is turbine 1. The output pressure of the turbine 1 is 1.2 megapascal. Next is turbine 2. The output pressure is 10 kilopascal. And next is the valve. If you remember, we said the valve is to decrease the pressure to the condenser pressure, so the output pressure should be 10 kilopascal. And click on next. We have all the information that we need. We click on OK to run the simulation and see the results. Now the results are available. We can briefly take a look into the results in the main flow sheet. We can check the box for the temperature and pressure, maybe mass flow rate, and also heat and work. So you can see that the temperature of the extraction is 306. 10% is extracted. It's converted to saturated liquid. So with a temperature of 12 bar and 188 goes to the valve and the pressure decreases to same pressure of the condenser, 0.1 bar. The temperature of the feedwater, as you can see, is increased from 51 to 159, which goes to the boiler afterward. So we have two turbines, two works. We have the Q in the boiler, Q out in the condenser. We can modify the calculator that we had from a previous simulation in our design. So you go to the flow sheeting flow sheeting options, and the calculator. The input should be changed because now we have two turbines, so we need to add another uh, uh, variable here. So I copy the work of the turbine and then I paste it here. Let's call this work of turbine 2, and this one work of the turbine 1. In the work of turbine 1, we check this that we have the right block, which is the turbine 1. We have one pump, so this is fine. Queuing is fine. Efficiency is an export variable. We want to calculate it, and WT2 is the work of turbine 2, and it should be import variable. You can move this up if you want by clicking on the move up, but that's not very important. So we can do it like this. So work up the, and this was, we need to modify this. Here we need to rename the variable. We can delete and add it one more time. Doesn't work like this. So this is efficiency. It's dimensionless. It's a parameter. Let's say it's parameter number 1. The physical is, it's dimensionless, unitless, and then it's export variable. So now we have all the information here. We go to calculate tab. Efficiency is minus work of turbine 1 minus work of turbine 2. We use a minus because the value that is calculated by the Aspen is a negative value because the work is produced. So we add the minus before that. Everything else looks fine, and the sequence looks fine. And then we can rerun the simulation to find out how much is the value for the efficiency. So we go to the results for the efficiency, define variable, and here you see that the efficiency is 33.1, which is 3% more than the ideal Rankine cycle without any preheater. So thank you very much. We will continue in another video for more simulations related to Rankine cycle.